Hi, this is Mr. Yeager for AP Physics 1. We are looking at another problem to do with the work-energy theorem. Definitely going to come into play here. We can see we have this marble. It's going to be sliding down the ramp here, going up and back down, a little track basically. Okay, and we have the mass of this bead. I'm going to keep calling it marble. 5 kilograms. It's released from point A, slides on the frictionless track shown above. I do like how this is noted. The bead slides, it doesn't roll, all right? And so that's kind of one of those weird things to think about as well. We're actually not having these things roll. When you do roller coaster problems and they're going up and down these tracks and it says that there's no friction, they actually don't roll. They're going to slide along the tracks, okay? And that's important because later on we're going to add rotational energy in another unit, okay? So anyway, jumping right into it. What approach can be used for this particular problem? Oh, look at that, I did that again. Okay, so what can be used for this particular problem? Okay, and so it's saying, okay, can you use kinematics? Okay, do you have to use kinematics? Is that the only way you can do this problem? All right, which means I have to use one of the kinematic equations. I need to know x, t, a, v, f, v naught. Okay, do I only use the work energy principle? Okay. Or can I use both? Can I use either one? It doesn't really matter. And so the thing is, how do I know when I can use one versus the other? All right. As we talked about, energy can be used in pretty much any situation. So the answer is you always are going to use the work energy theorem. You're really narrowing it down to just the work energy theorem or either kinematics or work energy. I think the only time kinematics would be appropriate is probably you just only have time. I mean, I could believe that, like, you have time and distance would be maybe the only thing to do there. But most likely, energy can cover kinematics. The issue, though, is can I use kinematics in this problem? All right. And what we talked about was kinematics can only be used if you have one acceleration. Okay. Kinematics can only be used if there's a single constant acceleration, all right, in the problem, all right? And I get it. You could technically find multiple accelerations and put them all together and stay using kinematics. That's overcomplicating the problem, all right? So all you're looking at here is if you have one acceleration, you can do kinematics and work energy. If you have multiple accelerations, you have to use work energy. And how do I know I have multiple accelerations? The height of the ramp, not the height, the slope of the ramp is constantly changing. So my acceleration is constantly changing. So the answer is I'm going to use the work energy theorem in this one. Okay? The work energy principle would be best. So that leads us to my next question. Calculate the bead's speed at point B. Okay? So I want to know how fast it's going. All right, so let's make sure we go back and take a look at this real fast. All right? Struggling with my board a little bit today. Calculate the bead speed. So again, it's released from rest. So this is going to be a work energy problem. So I'm going to be going back to the formula. Initial potential energy plus initial kinetic energy plus work external equals kinetic energy final plus final potential energy. That is the main formula to go with. That's the formula we're always going to look at. Again, that's the one I go to for any motion problem that I start with and then go, oh, need to maybe go back to a kinematic formula to make it a little bit easier. Okay? But for this one, we know we're going to use this formula. So calculate the bead speed. Well, I have a height. I'm 5 meters above the ground, so I have initial potential energy. The object starts at rest, so there is no initial kinetic energy. There are no outside forces. It's frictionless. So there is no work external. All right? There is no work external. At this point, I should see the marble move. So I have final kinetic energy, and usually the mistake I see people make is they don't realize, hey, at B it's still above the ground, so you actually still have final potential energy. So if I do the whole problem, I'm going to write out mghi will equal 1/2 mv squared. I'm going to write Vf just to be more specific, plus mghf. And now I just plug in all the numbers I know. But wait a minute, what else do I notice? Do I have to plug in every number? No. What can I cancel out? I can cancel out all of the masses. So I don't need to plug mass in. Can I cancel out G, which I see a lot of people do? Nope. There is no G in the kinetic energy formula, so I have to keep it. So let's go ahead and plug this in. It's going to be 10 times the initial height of 5 equals 1/2 times v squared plus 10 times 3.2. Okay? I'm going to speed this up. I'm going to go up to the top so I have some space here, so pay attention up here. It's going to be 50 equals 1/2 v squared plus 32. So this will equal 18, 1/2 v squared. Obviously, you don't need to go, I'm trying to show every step to make sure we're clear. This is going to be 36 times equals v squared, and so v will equal 6 meters per second. 6 meters per second. That is my final velocity at point B. So that's B. Let's move on. Determine the bead speed at point C. All right, well, it's going to be the same thing again. Let's go ahead and zoom on through this. It's going to be the exact same setup. Oh, this is the big thing here. This is what I probably need to make sure I say. All right. Where do I start? Okay. I want to determine the speed at point C. So the idea is I want to end at C. All right. And so this is something I do see students sometimes do. They go, okay, well, I now know the speed at point B, so I'll continue using that and keep moving forward. That's fine. That's fine. My recommendation, though, is if this is noticed, there are no external forces on the system. All right? None. Which means it's path independent. It doesn't matter which way you go. Okay? It doesn't matter. Energy is going to be conserved from every point. So I can go from A to C on this problem, which is what I'd actually recommend. All right? Because obviously, if you go from B to C, you're going to have initial potential energy, initial kinetic energy, final potential energy, and final kinetic energy. So you're going to have a few more numbers. Is that wrong? No. No. It's not wrong at all. Okay? The only thing that might happen, that hopefully it doesn't, is what happens if you accidentally did a calculation error here. Then you're definitely going to get it wrong. But if you start from the beginning and go A to C, okay, it doesn't matter what the path is. All right? We can get the same answer. And so that's what I would recommend. I'm going to go from A to C. So that means, again, I'm starting off with initial potential energy and switching to final kinetic and final potential energy. All right, what's going to happen is the final potential energy will be less, which means more of it will go into the kinetic energy. And so if I do this problem again, mghi equals 1/2 mv squared plus mghf. I'm going to go a little faster this time. Masses cancel out. I want you to see that every single time. That's really important. This will be 10 times 5 equals 1/2 times v squared plus 10 times, what was that number? 2. All right. I can solve. This is going to basically come down to what? 30 equals 1/2 v squared. So we got 60 equals v squared, and v will equal, what is the square root of that? It is 7.7. 7.7 meters per second. Okay? Which makes sense. More of it has changed to kinetic energy. I am lower. There's less potential energy. It has converted into potential energy, but the mechanical energy is still the same. All right? So now looking at part D. Determine the net work done on the bead and moving it from A to C. And I'll see a lot of people go, well, the net work is 0 because there's no external forces. Wrong. Okay? That is incorrect. There is work being done. What are we changing? We are changing potential energy to kinetic energy. I understand it's all within the system. It's all within the marble earth system or bead earth system. Okay? But the thing is, you cannot change one energy to another type without work being done. So what do you have to do? I need to figure out what was the initial potential energy, okay? And what is the kinetic energy at this particular point? Okay? How much energy changed? You could do it that way, or you could actually figure out the change in heights. I mean, there's multiple ways to do this. So actually, I'm going to go this way. I'm going to say the work done is the change in potential energy, because that's equal to the change in kinetic energy. So I can do this as work equals, this one I do need to keep mass now. It's going to be mghf minus mghi, okay? mgf and mghi, okay? This will equal, what is the mass of this thing? 5 kilograms. So I'm going to pull that out. It's going to be 5 times 10. I'm going to pull mg out and do, what is this? 2 minus 5. 2 minus 5. Just double checking. That's correct. Okay. And so you can see what we get here. It's going to be 50 times negative 3, negative 150 joules. All right. You can say that. That's the net work done on the bead. All right. It's 150 joules. Whether it's negative or positive, it doesn't really make that specific. I would leave it just simply as a positive number. All right. But that is the work that's done on the bead. Okay. 150 joules of work. And that's actually the amount of kinetic energy. If I do 1/2 times 5 times 7.7 squared, it's actually going to be 150 joules, I believe. All right. So I actually want to double check that real fast just to make sure I am not making a mistake on that. Okay. I think it's understandable that mistakes occur, and we just try to learn from those all the time. So, yep, I got 148, so close enough. Okay, close enough with it. All right. So we still have, I think, one more section here. Oh boy, 2 more sections. Okay. Now you have a similar bead of mass 2.5 kilograms. So you went from a 5 kilogram bead to a 2.5 kilogram bead. It's released on the same frictionless slide. Will the speed of the ball at point B be greater than, less than, or equal to the speed you calculated in part B? Okay. So we're trying to go, okay, what's going to happen with the speed of the ball? Let's think about this, guys. If we're at point B, again, we're doing the same thing we did before. mghi equals 1/2 mv squared plus mghf. We're trying to calculate the speed. But what happens to the mass? It cancels. And so guess what? Will that change the speed? Are any of the other numbers changing in this problem? No. Same height, same gravity, same 1/2. And so guess what? The speed of the smaller object will be the same. And why is that? Mass cancels out. Mass cancels out of the equation. All right. Now the thing is, and they go to, will the net work on the new bead in moving it from A to C be greater than, less than, or equal to the net work you calculated in part D? Okay, will the net work be the same, or greater or less than, equal to? This one, though, takes us back to letter D, as it says. If we look at letter D, did mass cancel out? Mass does not cancel out. And so therefore, I'm going to be plugging in a smaller mass into this problem. This number right here is going to be 2.5 instead of 5, which is going to do what to my overall work? It's going to decrease it. And so therefore, the net work will be less on the smaller bead because mass is in the formula. Mass is in the formula. It's actually going to do half of the work. We're using the formula mg delta y, the change in potential energy, which equals the work. If I half the energy, half the mass, I'm going to half the amount of work being done. So it's definitely going to be less there. All right. So another pretty good problem going through, and I wish you good luck on any other problems you have to continue working on. Thank you.